Stored programs have both data and instructions stored in memory. So we can access the instructions by reading memory and also access data by reading memory. A program is just a sequence of instructions. So the power of this stored program is that we can change what the program does, what the computer does, just by changing the program, changing the instructions located in memory, as opposed to where I have to create a new design for each application I want to make. Instead, we have to just change a new program. We don't have to rewire anything, and we simply change the program in memory. To execute a program, the processor fetches or reads instructions from memory in sequence and performs specified operations. So here's an example stored program. We have the add instruction followed by the subtract, and we convert those assembly instructions into machine code, and then that machine code is loaded into memory. Here's memory, here are the addresses. Remember, the addresses are increasing as we go up. So here's the add instruction, and the next memory location, or 4 bytes later, right, a word later, is the subtract instruction, and then later is the add immediate instruction, and finally the load word instruction. And so the PC, or program counter, keeps track of the current instruction executing. So when this program starts, it would start at the PC being equal to hex 830. So PC starts at being hex 830, and then it's incremented by 4, and the PC then becomes hex 834 and fetches or reads that instruction from memory, and then increments by 4, PC increments by 4, and now the PC becomes hex 838, fetches that instruction from memory, right, reads the instruction at that memory address, at the memory address pointed to by PC, or the memory address of the program counter, the data pointed to by that PC, and then finally PC increments by 4 again to hex 83C, and we read memory at that address. That is the memory at that address is an instruction in this case, and perform the operation indicated by that instruction. In this case, the last instruction is the load word instruction. One of the influential members of computation was Alan Turing, and he is considered the founder of theoretical computer science. He invented the Turing machine, a mathematical model of computation, and invented one of the first stored program computers. Unfortunately, his time and his contributions were cut short by his being prosecuted for homosexual acts and then dying of cyanide poisoning shortly thereafter. The Turing Award was named in his honor, which is the highest honor in computing. So how do we compile and run a program? Well, we start with our high-level program written in C, Java, etc. We compile it, so it's compiled by the compiler into assembly code, and the assembler takes that assembly code and turns it into an object file, which is basically a machine code, but there may be other object files, so we may call a function in a library, or may have 2 files that contain our code, and so then those object files are brought together by the linker and turned into an executable, which is the machine code for that program, loaded into memory, and then run. So Grace Hopper was also one of the founding members of computer science. She graduated from Yale University with a PhD in mathematics, developed the first compiler, and helped develop COBOL, a programming language. She was also a highly awarded naval officer and received many medals for her service. So what is stored in memory? Well, instructions. This is also referred to as text, and data. Data can be global or static data, which is allocated before the program begins, or dynamic data, which is allocated while the program executes or runs. So this is allocated via malloc or new in our programs. How big is memory? How much memory can we access? Well, we have 32-bit addresses, so we can access at most 2 to the third 32 equals 4 gigabytes, or 2 to the 2 times 2 to the 30, or 4 gigabytes of memory. So we can address from byte all zeros to address hex FFF, all Fs in our 32-bit address space. So this is one of the reasons why there's been a push for 64-bit processors operating on 64-bit addresses, so we can access up to 2 to the 64 bytes of data instead of just 2 to the 32. So here's an example of RISC-V memory map. We have our text segment, which is where the instructions go, and our global data. This is for global or static variables. And we also have our dynamic data section. The stack grows down from higher addresses. This is the data that's dynamically allocated throughout the program execution. And our heap, which is for dynamically allocated data using new or malloc, for example. And we also have some reserved sections here, reserved for the operating system and I/O, input-output, and exception handlers here shown on the bottom in the lower part of the memory address space. This is the memory map, and we also have registers associated with these. So the PC, these are this PC register is not part of the register set. So PC, or program counter, keeps track of the current instruction being executed. GP, the global pointer, gives the address of, well, some location, typically the center location of the global data. And SP gives the, as we've talked about, the stack pointer, the address of the top of the stack. And remember, the stack grows downward. So let's look at an example program and follow it through all stages of compilation and then loading and running the program. So here's an example program. This one's written in C code. We have some global variables, F, G, and Y. And then we have a function that returns an integer. And we have the main function, which assigns F to 2 to F, 3 to G, and then calls func with those operands, F and G, and then returns. So first, this code is going to be compiled. The first step in running a high-level program is to compile it into assembly language. So the compiler takes the high-level code, written here for your reference, and converts it to assembly code. So here we have the assembly code on the left and the address, the memory address, here on the left as well, on the far left. And so the first thing the program does is take the stack pointer and decrement it and store some registers on the stack. So RA and S0 are going to be used by the func function. And so the program makes room on the stack and stores those registers on the stack. And then A0 is put into S0. So A0, remember, is the 0th argument of the function. In this case, A is put into S0 because it potentially could be used after a function call. And so we're going to put that into a saved register, so it will be preserved across that function call. And then add A1 and A0. So add A1, which is B, and A0. This line is doing A plus B, and putting that into the return address register. Remember that A0 has two kind of purposes. First, to pass in the 0th argument of the function, and also to hold the return value when a function returns. And so this performs A plus B and puts the result into the return register A0. And then branch if greater than or equal to 0 checks the opposite case of the high-level code. High-level code checks B less than 0, and branch greater than or equal to 0 checks if B is greater than or equal to 0. If it is, it branches to, in this case, hex 1016C, which is where the else block is located. But if that branch isn't taken, that means that B is less than 0, and the stack is, the registers are restored from the stack pointer is restored, add 16 to it, right before it was decremented by 16. So restore the registers and the stack pointer, and then return. And return is a pseudo instruction for JRRA, or jump register RA, the return address register. But if this branch is taken, so B is greater than or equal to 0, right, here's B, A1, the first argument, so 0th first argument, right, here's our 0th argument and our first argument. That branch is taken, then B is decremented by 1. This is this part, B equals B minus 1. And then S0 is moved into A0, so A here. And then this func is called again with now arguments A, and instead of B, B minus 1. Once that function returns, then the return value is going to be held in A0 by convention. And so the function then adds A0, that return value, with A. And remember, we put A into S0 before the function was called, and so we know that the saved registers are preserved across function calls, so S0 is going to hold the value A across a function call, even when that function returns. We have A plus the return value from when func was called, and we put that into the return value register. And then this function jumps to hex 1015C, which restores registers from the stack, restores the stack pointer, and returns. One thing to notice is that the stack pointer decrements by 16, but the program only stored 2 words on the stack, so it really could have decremented by just 8, right? SP minus 8 instead of add I SP minus 16. But RISC-V requires that the stack pointer maintain forward alignment. So we made room, or the program made room for 4 words instead of 2 because of the forward alignment. And that is to maintain compatibility with RV128I. So what we're talking about is RV32I, operating on 32-bit data. But RV128I operates on 128-bit data, which requires 16 bytes per data value. And so to maintain compatibility with that, we decrement SP by forward increments, so 16, 32, so on. Also notice the pseudo instructions. We have the move instruction and also the return instruction. The move instruction is translated to add immediate A0, right? We're moving what's in S0 into A0. Add immediate A0, S0, 0. Here's the main function compiled into RISC-V assembly code. And here's the high-level code on the right for your reference. So first, the main instruction makes room on the stack and then stores the return address on the stack. It's going to call a function. It's a non-leaf function. And then it loads the constant 2 into A4. It uses the pseudo instruction load immediate, but because 2 is such a small immediate, it can use the add immediate RISC-V instruction. So f equals 2, so puts 2 into A4 and then stores A4 into the memory location that's been allocated for the variable f, and does a similar thing for G, puts 3 into A4 and then A4 into the memory location allocated for G, which is hex 101A34. And then finally loads the argument registers puts G into, or the value of G into A1 and the value of F into A0, and then calls that function, JAL func. And then after it returns, right, it's going to return to PC plus 4, which is hex 101 A4, and it will store, right, A0 is going to hold the return value, and Y is going to be assigned to that. So A0 is going to be stored into the memory location allocated to Y. And finally, RA is restored from the stack pointer is restored, and the function, the main function, returns. And remember, return pseudo instruction for JRRA. So one thing to notice is that the global pointer, so here's a register, one of the registers in the register file, the register set, has to be 11DE0 because F is allocated this memory location, hex 11A30. So GP plus a negative, or GP minus 944, well, 944 is hex 3B0. So 11DE0 minus hex 3B0, that gives us the value, or that memory address that we want. So the global pointer, in this case, is pointing at hex 11DE0. After the high-level program is compiled into assembly, the assembler takes the assembly language and assembles it into machine code. So here shows the assembly code of the program, and then the corresponding machine code and the instruction addresses. So for example, the add immediate SP-16 has the machine code hex FF010113. And at this point, these pseudo instructions, for example, return is converted to JRRA, the move instruction is converted to the add immediate instruction, and so on. Each program also has a symbol table, and the symbol table indicates, well, the symbols, and symbols are labels and variable names. And so the symbol table indicates the address, for example, func starts at address hex 10144, and it's part of the text segment, so that text indicates part of the text segment, and its size is hex 3C bytes. That's how big it is, how many instructions it includes in terms of bytes. The main function starts at address hex 10180 and has 34 bytes of instructions. F, G, and Y are each 4 bytes, and F is located at hex 11830, G is next at hex 11834, and Y is next at 11838. And now the loader loads this program right before it's executed, loads it into memory. And so the instructions, here are machine instructions, are loaded into memory at the locations indicated. So for example, here's our main function starting at address hex 10180, and the func function is right before that at hex 10144. F, G, and Y are located in the static or global data segment. PC is initialized to the first instruction that should execute, which is the first instruction of main. It's our main function located here. Remember, addresses grow from the bottom to the top. They get higher as we go up. And the global pointer is initialized, the stack pointer is initialized, and now the program can execute and start fetching instructions starting at PC. That program is fetched into the processor, executed, PC is incremented by 4, and the new PC becomes 10184. That instruction is now fetched into the processor or read from memory and executed, and so on until the program completes.